Good morning, everyone. I would like to welcome you for our sixth webinar. We talk about the arc flash risk assessment and common myths. So that's my plan for today. If you know me, that's fine, that's good. I hope you do. But if you don't, you might look into my profile LinkedIn. My name is Marcin Ruta. I'm the power consultant. I'm dealing with the electrical engineering last 15 years, and especially with arc flash risk assessments for the EMEA region mostly. For today's webinar, keep it quite, sorry. To keep it simple, we will keep it under 13 minutes. And then we have Q&A session. It's not 15, it's up to until we run out of time or questions. And I'm recording it, as you can see, so we can share it later with everyone else. For today, I have a simple agenda. We will talk about the arc flash myths. And the reason why I think it's good to talk about it is because I think it makes a lot of problems and misunderstandings in our field, especially when it comes to safety. What I did, I thought it would be very nice to make this approach when I can tell you if something is a myth, if something is true or is a gray area. You will see it in the right top corner. Why I think it is a problem in generally, because as far as you can see, it's for me is a problem that it is hard to spread the knowledge, especially when you have very strange myths behind people are stick to it, and it's hard to change their mind. It's very comfortable if you are living in your safety bubble because you don't have to do any safety updates. You are not interested in any actions because there is no problem, of course. And if needed, generally people are like to adjust the risk to the situation just to show it's okay. And for me, it's like personal safety debt that will have to be paid typically by someone else. So I thought it would be a good idea to go through the myths. Probably I miss some of them or a lot of them. So leave me the comments, leave the questions here so we can address it properly. And let's go to the first one. So I hear very often, especially in Europe, that when we talk about the arc flash, it's a US standard only. It's only applicable for US, and we don't care about it. And I keep it as a gray area because it really depends. So definitely it is US origin. All the methods, guides, and standards are international. So it's not that it's only for US. And obviously they have NFP 70E standard, which is National Fire Protection. It is based in US and it was starting there more than 30 years ago. Of course, we have IEEE 1584, which is Institute of Electrical and Electronics Engineers. As you can see on the map, it's not only US, it is a worldwide organization. Which probably it started in US, but it's now international. So it's hard to say it's only there. From a European approach, like for Europe, if you look, we have a ESA guide, which was submitted many years ago, which is talking about the arc flash. The DGUV 203.077, so the approach from Germany, Deutsche Gesetzliche Unfallversicherung. It's also kind of guide. It's in Canada, CSA. It's very similar to NFPA, but it's not identical. And I will talk about more because there's also in Australia and so on. So now definitely it's not only US. Similar question. It's not in EU, so we don't have these requirements. And it is not true, simple, because we have. And if you look from the US perspective, yes, we have the requirements. It is under EU regulation 89391. It is very general, this one, but also we have EN 1510, which has Annex B6, the latest revision. And Annex B6 generally address the electrical safety hazard from arc flash. And this standard is harmonized in each country in specific way. Sometimes it's one-to-one, like the cover standard. Sometimes it's adjusted to the site's country-specific regulation. So you see it's in Belgium, Netherlands, in UK you have British standard EN 5010, and also electrical at work regulation is in Italy, in Sweden, France, Germany has DGUV, NFPA in US, Canada. In Norway, as far as I know, there is no standard, but there is a regulation from Equinor after the accident, GL07, for the all marine business. Lloyd's has it, American Bureau of Shipping has it, not everyone. Australia, New Zealand, and probably I skipped something, but that was what was as far as I know. And the second part of this question is, if you would like to know more details, so it is written that we need to evaluate the risk in general. So it's not risk specific, the regulation from European Union, EEC. We have to combat the source, we have to make the policy and so on. But EN 5010 is much more specific. It generally says, if we work in visiting the electric station, we are exposed to a hazard caused by an electric arc. And more, you can read it, everything, but it is written there. It is referring NFPA 70, even IEEE 1584, as a good source of information. So it is not true, as we have it in Europe. This is a little bit different. So ACRA study in US. So it's hard to call it as a myth, but it's more like question that when I hear it sometimes from time to time, if ACRA is obligatory in US. So if you go step by step, it might look that it's not obligatory to make ACRA study, but you need to assess your risk. You need to assess the hazard and estimate the energy and so on and so on. So that's what OSHA is telling you in 1910-69, appendix Z. And also there is the second table there where it's saying what kind of method is applicable to what kind of voltage levels. And you also have it written now in NEC, National Electrical Code, in Article 110.16, and IEEE 1584, NFPA 70. So probably you might fight with the word, is it obligatory or not? But I would say 99% of cases in US, you can treat it as it is. So I'm not sure if you can win in court saying that you didn't do the study, you did something different. But in my feeling, it's much easier to follow the OSHA requirements, fulfill the NEC requirements and NFPA 70E just by doing the ACRA study or following the table method estimation than just not doing anything else. This is something which I like. I hear it quite often here in Europe. So the question is, like, it's a question or myth is, like, we already have ACRA's PPE, we bought it and we are protected. And the simple answer is not true, because the more specific question is, how do you know that your PPE will protect you? Because if you never did an estimation of the hazard, you don't know your numbers, how do you know it will work? So PPE is something we match against the hazard. So we try to be quite specific to match it, not to overprotect, not to underprotect, just to go to the point. And I hear it very often, like in Europe, for example, we use PPE very often. You can hear we use PPE class 1, class 2, which is box method testing. Not popular in US, it's popular in Europe. And you very often hear that people will tell you we have PPE class 2 for medium voltage switchgears and PPE class 1 for low voltage switchgears, and we are safe. And in fact, it's completely opposite way, because you very often expect much higher energy on low voltage switchgear or installation than on the medium voltage. So the selection is not correct, but despite the fact that you don't know your numbers, you don't know the incident energy, you don't know if this is 0.8, 40 calories, or maybe 100 calories. And in US, maybe you can, or with ATP word, you can see something like PPE category 2, up to 8 calories, when people say, oh, we bought some basic PPE and we are done. I think it's mainly driven by PPE suppliers when they really would like to sell something, and but the customer doesn't have any clue or doesn't have any study and don't know really what to buy. So they will go into the middle and say PP category 2, 8 calories or 12 calories as a solution for everything. So you might, if you don't have anything, go to the NFPA 70. There is a table where you can use estimation, what kind of PPE category you need. Okay. Arc flash is only for the big panels. I hear it very often. Is it medium voltage, low voltage? Is it like 2000 amp panel or 4000 amp panel on the low voltage side? That's what people focus most often. And it makes sense to start there, but technically we go down to the, generally we go down where we think the arc flash might happen. So in IEEE, there is a rule from 2018 where after multiple tests, they find out, yes, down to 2000 amp short circuit current level at 208 volt, we can sustain the arc. And this simple means that even the small panel like this one might be above 1.2 calories. So we need to include it. So as a rule of thumb, I can tell you that from the practice from the projects, if you look on the main switchgear, yes, of course, we have to check it because it's very unlikely that it will be below 1.2. So that's okay. But it's not limited only to this main panel. It's downstream distribution boards and panel boards as well. Because I can give you an example from the story I have from the multiple sites. Such panel might be fire protection panel, which is connected directly to the transformer, because that's how it is designed. So the protection for this one, for the upstream side, it's a medium voltage protection sometimes. So usually there will be very, very high energy, surprisingly high energy in the small panel like this. So now it's not true. It's not only for the big panels. We go down to the machine level most of the time. We don't work live. So this is half true. And I hear it it's like cutting corners in the way how you think. So as per NFPA 70, also EN 5010 about the electrical safe procedures, we need to establish electrical safe conditions. So we need to prove absence of voltage, sometimes install temporary grounding, and all of this is treated as a live work, because absence of voltage testing is the point where we will measure if the voltage is there or not. If it will be there, it is live work. So we will need our PPE for doing this. And all the measurements that we have to do sometimes on site, it is considered live work. There are some solutions how to go around this, but it's not that the fact that you switch off the breaker before the work doesn't mean that you will not work live for a certain amount of time. Low voltage systems are safer than medium voltage systems. So it depends. It's not myth, it's more like understanding. So from my evaluation point of view, from most of the projects, it is opposite way. So your systems will be on the low voltage side, it's usually much higher energy than on the medium voltage side. It's not because of the physics, it's more how we design our electrical networks. So I can show you an example from the tests. So this is the test from medium voltage. It is test for internal classification, but at least it gives you some idea. And I want to come back to this as well later. So you might see this. I think it's quite straightforward when you can see how the things behave. And very often on the medium voltage installations, we have lower currents, lower short circuit currents, and eventually the energy will be lower. But this is more from, as I said, from the way how we design. The same test, it's very similar test. Of course, it was failed just for the purpose of testing, but it gives you some idea that generally there is more arc flash energy available, possible to happen in the low voltage systems. It is happening, and I have to explain this a bit more. It is happening because of mainly because of this. So if we look on the medium voltage or low voltage systems, let's say this is 11 kV, this is 400 volts. There is a relation between the short circuit current, which is bolted fault, when we just have normal short circuit current in the system, and arc flash current. And in medium voltage system, the arc flash current will be almost the same as the short circuit current. That's because of the arc geometry, which is okay. It's maybe bigger, but overall voltage drop is generally relatively small to the, let's say, 11,000 volts is here. If you have 1,000, will be approximately 10%. That's it. And the current is lower, arc flash current. So we have a short circuit current, which is 100%, arc flash current is 95%, and our protection device see more or less the same current and can trip more or less the same time. For the low voltage system, it's a little bit different because it can go down to 37%. So if you have 100,000 amps for the normal short circuit current, for the arc flash it might be 37,000 amps, and it might also say that your protective device will see smaller current and will not trip in 100 milliseconds. It might trip in 2 seconds. So this is a problem generally for the low voltage systems and the arc flash. So low energy is not a problem. So this is generally, again, cutting corners. So it's not true, because if you have something like 2 calories, 4 calories, 3 calories per square centimeters, or 1.4, 1.5, you might hear people say, it's not a problem, it's a small one. Well, technically it's not, because everything which is above 1.2, so above the Stoll curve, which is the green one here, which was generally developed by Alice Mary Stoll and Maria Chianta in late 60s. So this means that everything above this time, this energy will tell you about the heat flux, will tell you, okay, our skin will be burned more than 2nd degree burn. So this is called time to 2nd degree burn. So if we hit this above 1.2, we have more than 2nd degree burn. So you can imagine that if you don't have a PPE and you have 1.4, you still will have 3rd degree burn. And of course, if you have 40 calories, it will be much worse. But it doesn't mean that it will be good at 1.4. It's more like it's bad, very bad, or very, very bad. This is something I like. That was the previous webinar that we discussed. New installation is safe. So you just take it as a granted that you replace the switchgear, you spend a lot of money, and you tick the box that we retrofit all the installation with the new one, and our problems are gone. So you don't expect any issues. I think what I can blame a bit is probably the sales guy from the switchgear manufacturers, I think, or generally this kind of, I used to be in the business, so I think that's probably what I can do. But it's also about the understanding. So if you replace something 1-to-1, like this old one and with the new one, of course, from shock hazard point of view, and that's what is really good about it, it will improve, because it will be new and there will be all sections, covers, everything in place if it's done well. So it has to be improved in shock hazard, from shock hazard point of view, and that's a very good thing. But if you look from the arc flash point of view, if you replace something 1-to-1, there's almost no difference. And from the calculation of the results. So in fact, you might spend a lot of money just to see that there is no huge difference on the results at the end. And what I might say, it's always better to consider any retrofit or modernization. That's a good thing, but if you consider it, make all the studies before, not after. So the previous webinar that I was doing, that was this kind of project when it was everything replaced with the new equipment, new switch gears, and at some point we did the arc flash study. So when it was already installed, and I found out, yeah, it was almost 1-to-1 replacement, all the settings, everything else, and eventually the results were very similar, or actually bad. So we have to start to find a proper answer how to solve it, and we end up with the arc flash protection. But generally, if you order new switchgear, don't take it for granted that you spend a lot of money and it will fix everything. It has to be done by, you need to have a reason to do it, to spend it. You need to know what will be improved. And if you don't have an arc class study for it, or protection study or selectivity study, so you're not sure how far you improve things. So that's important. We can't work live. So that's a similar question that we had before. And I also hear it, that it's forbidden. But no, it's not. It's not true. There is a way how to work live, and the whole transmission system operators, TSO, and sometimes distribution operators, they work live. I even know companies that they work live in industrial systems on big factories. And it is possible. It's actually, when I talk with the people from Polish TSO, they said, yeah, when they introduced in, I think, late 80s or 90s, they found out that they had less accidents. So the way how we work, as you see on the photos, it is possible. There is a whole procedure for it. It requires some additional advanced training for live working. And you also need some proper tools. You need some proper PPE. But I think the difference was that when you start to work live like this, you know that the hazard exists. There is no discussion if it exists or not, and we are safe or not. But you know that there is a source of hazard. It's energized. So you need to do everything in a way that you will not hurt yourself. But it is not recommended if not justified. Usually justification is the time, money, and some improvements on maintenance. But it's not true that we cannot work live. We cannot work above 40 calories per square centimeter. This is something which I hear very often. So it's not recommended. So one thing, it's not true. That's one thing. We can. Again, because it was, I think it's historical thing coming from US for a very long time, and still now, you cannot buy PPE above 40 calories. So as far as I know, in Europe, we can buy PPE up to 100 calories per square centimeter, and in US it is up to 140 calories per square centimeter, and purely made, as far as I know, from Oberon company. And there was a discussion behind it that such big energy might release very big arc blast. And it's kind of half true, because arc blast is not directly related with the energy itself. It's more related with the short circuit current. So we need to have very high short circuit current in very short time. And the high energy might be just the result of very long time. It might take 2 or 3, 4 seconds. So as far as I know, arc blast pressure is not, as far as from my perspective, I haven't seen any case proven that arc blast killed someone. On the other hand, it's quite hard to protect yourself against arc blast. So technically it's not true. We can work above 40 calories if it's needed, because we have PPE up to 140. And there are locations sometimes where you might need such PPE to just do something, like electrical furnace or in glassworks. What I can add to it, the fact that we can work above 40 calories doesn't mean that we won't. It's not recommended. So we generally try to limit energy down. This is the situation when we run out of options and we cannot improve it. But it's a rather rare situation. So we try to keep energy below 40 calories, and that's why we focus on recommendations every time. PPE to enter substation. So I think we had the discussion yesterday somewhere on LinkedIn, and it depends. It's not true, not mistrue. It's more about what kind of location we talk, site specific. So what you might look at is, if we talk about the shock hazard and arc flash, because when we talk about the shock hazard situation, it might be that the PP is actually needed to enter substation. If we talk about the medium voltage on high voltage substations, we might expect higher ground potential rise. And then, for example, we need insulation boost just to enter the area of the substation. So if someone is not authorized personnel, he shouldn't go there. When we talk about the arc flash related hazards, just to enter the room, normally it's not required to have any arc flash PPE. So let's say, I can tell you a story. You just go into the substation, low voltage substation, and everything is fully enclosed, normal operation. So you don't have any exposed bus bars or transformers inside. So you just want to go there, I don't know, have a look if you have extinguisher there and the date is okay. So do some simple inspection. And just to enter the room, generally you don't need any arc-rated PPE. But it might be that you have already identified very high incident energy and you decided as a site that your minimum PPE, just daily work, is 12 calories per square centimeters, then you already have it. And that's thing related with the situation when you go there, you start, okay, now I would like to do something, and you have to come back to take all your PPE and come back again to substation, do your work, then come back to the office, drop the PPE. So typically, this is like the PPE strategy than real requirements. So I would say it depends really on site-specific situations. I'm the fan when the daily worker clothes are up to 12 calories per square centimeter, because it fixes a lot of issues and it makes it much more easy to use. You get used to wearing this PPE because they are the same as normal one, and you are protected at the same time. And then we don't have this question if you need PPE to enter substation or not, because you already have it. We need PPE for switching. So again, it depends. In an FPA, you will find in the table on the left side, you see the name and type, that technically we don't need PPE. If everything is normal, is properly maintained, so normal operation, normal conditions, we don't need PPE just for switching. Normally it's identified with very low likelihood for things to happen. And generally will say, well, we don't need PPE for doing just this. But if you see on the pictures that I took from the one sides, I think 2 sides, that you will see that there is a difference between switching this breaker and switching here. And what you don't see here, there were bus bars, copper bus bars on top of this one. So that's why I wear PPE every time I go on site. You don't see there were top bus bars when cables were connected down to everything here. So for switching this one, you will need PPE because you will be directly exposed to the live copper bus bars. And if you look on this one, you don't need your PPE. Withstand and voltage rating. So we have to catch up a bit because we are running out of time. Withstanding issues. So if you never check in your installation that we don't need checking the equipment evaluation if our equipment is properly rated, it was designed well, and so on, that's fine. If you have a document that is telling that against the short circuit current, which is 50 kiloamps, you have an equipment rated 65, that's fine. But if you have a 65 kiloamp short circuit current and your equipment is rated 50 kiloamps, that's not okay, because it might lead to the accident just for normal operation. So have a look. That's the recording of how the bus bars behave under the short circuit conditions. So this is not okay, obviously, but if you look at it, you'll see a lot of things happening and start, it might start arc flash just because it's not mechanically reinforced. Next one, which I really like, and I think I have to point it, that people tend to extinguish electrical fires with extinguishers. So generally they try to do something while it is still energized. So there is a difference if you, so this is not true. You cannot really extinguish electrical fire, but I need to explain 2 things. So when we talk about electrical fire, is the fire caused by electricity, and then, for example, electricity is switched off, and then you just extinguish the fire itself, or you try to extinguish arc flash. The first one is possible to do, the second one is impossible to do, and you put yourself in danger. So you always have to switch off the power. Otherwise, it's impossible to do. And just to show you example, that's how it looks like. So you see the arc flash, it is happening, it's not a big one, and you think you can put it down. So they will try. I think it's CO2 or powder. And you see that it's keep going. It's not disappearing. Because we still have a power, we still have a voltage, and we still have a source of energy for the arc flash to happen. So doing this is generally pointless, and if you have something like this, you cannot switch off the power, forget about it. Don't think about it, just go try to switch it off. You can put the fire down once the energy is, once the power is just is a secondary effect, is a fire. That's what you try to get rid of. Then interesting part here, have a look. This one stops and the next one starts here. I can't be fined. So this is interesting topic because as if you follow it in US, of course, they have fines. In UK, fines are much higher now, like 600, 1.5 million I've seen. In Australia, there was a last year fine for some small, I think there was serious burn, the young apprentice. And they also fine directly the directors. So not only the company, but directors as well. But on the other hand, on Equity Norway, there was a arc flash accident in the platform when someone was hurt. And actually, they were not fined. They just estimate the cause of this accident. But I dig out, for example, in Australia, in the Electrical Safety Act, it states up to 20 years of imprisonment. So I can drop the link to it, but it is not that we cannot be fined. It's more about how the government is approaching this. And we are approaching the end. So open, closed doors, no difference. It's not true. There is a difference. For sure, there is a difference if we have a closed doors and open doors sometimes, but you cannot take it as a granted, and we cannot really easily calculate it, influence of those. I've seen some kind of approach to it, but it's like very subjective. You just take the percentage number out of, I don't know from where, and I don't like it because it's better to keep open, close as the same. That's what NFPA is saying for a moment. That's purely because we'll have to go through all the FMEA calculations, which will be extremely expensive to do one panel. So because you need to take into account, is it fully closed with, if you have a 3 locks and it's closed with 2 locks, it makes a difference. Sometimes it's not closed at all, but most of the time on low voltage system, when you work with it and you start to open things, yes, it will be a difference, but eventually the worst case is the open door. So we treat generally open, close as open. And of course, you have all the small panels distribution boards, which are, if I go through the side, you see the flipping doors, closed, not closed, locked, not locked. It makes a big difference. And they are plastic or metal. It's an interesting point, which I would like to just highlight. So we have internal classified panel and we are all safe. So it's not true, because you need to be aware how this internal classification works. So we can have it for the low voltage, which is rather rare to see, but and very common to see is the internal classification for the medium voltage systems. So just fact that something is internal classified doesn't remove the danger and doesn't remove all the responsibility behind it, because you might do some troubleshooting. You might try to do some open doors measurements, and then you don't have this internal classification anymore. There are some certain rules behind it. So it's associated usually with normal operation and all requirement conditions like covers, doors, everything has to be placed, locked and secured. But also the test itself is done with, I don't know if you haven't seen this, but it's like 30 centimeters. You have a cotton rectangles around it, and we test if this ignites or not. Which means that, and I saw this discussion recently, if you stay here, this is, I think it's not past test, but generally if you stay here and something like this will happen, and you wear not cotton, but you have some kind of plastic-alike clothes, polycotton, whatever it is, polycarbonate, then it might burn as well. It might ignite, because we all test against cotton testers. So you have to keep in mind that it might be internal classified, and your clothes might still get burned. Very common, the high-vis, jackets that we wear are like almost like plastic. So this will burn. This will just generally burn and might ignite on top of you. And almost at the end, this system is okay. So it's not true, and these systems are they are very often overlooked when we look on the arc flash, also about the shock hazard. Sometimes they are they are more than 48 volts, but up to 100 volts DC is considered safe. But from arc flash point of view, even down to 48 volts, it was proven that we can sustain the arc and with quite high incident energy, above 1.2 calories. And this is for all the PV sides, DC networks, battery storage system, or UPS DC side and batteries, or EV cars now, which they go up to 900 volts DC recently, as far as I've seen. And that's that's the PV side. I dropped this video somewhere on LinkedIn before. It's very nice, shows you how the thing will go. And until it's switched off, you can forget about extinguishing it. It will just keep burning until it will burn out. And that's all for today. That's all the myths I had in head. So I will go through all the questions and the Q&A for you now, and let's have a look. So just a short summary. I'm doing some holiday break, so we'll come back in September. In the meantime, I really encourage everyone to sign in to my newsletter so you can receive information about the upcoming webinars, follow up from this webinar, also link, and I'll try to make a summary what we did up till now, so you can watch everything if you didn't do it before, and you can receive the information about upcoming webinars. You can also follow me on LinkedIn and look through my YouTube channel, where I upload all the webinars so far. And we think we still have 5 webinars to go till the end of the year. So let's go to the Q&A session now. So I will go through the questions and try to answer all your questions. Let me go through it. If we have something. Well, I don't see any questions yet, but you can keep adding, and what I can add. Oh yeah, it's from Antonio. For Italian technical issues, C1127 voltage detection via in 61234 is not a live work, and grounding and short circuit too. So you might as well check C1127 against EN5010, because grounding, if you install the grounding, the first point of grounding usually is treated as live until you ground everything else. So it might be different in Italian rules, but voltage detection, there are some specific hardware solutions that will make it easier, of course, so you don't check it directly. But you can imagine that if you have a stick and you check it in the medium voltage system, like in the old style, you prove it, then you need to have your PPE to do it. So it depends on application a bit. I'm not sure if I answered your question, but this is general rule of thumb. Yeah. So there are some hardware solutions to go around this problem, because it is you might have everything which is below 1.2, or maybe everything is still internal classified, but at some point you have to do those 2 steps, and then you need your PPE again. So in my feeling, it's good to, if you close the loop, put some hardware that you just do absence of voltage testing, not remotely, but let's say it's taken away from the hazard. So you just test it and you see if this is if the voltage is there or not. Simple, and you don't need any specific PPE for doing this. So that's like next step of improving everything else. I think it's coming it will be more driven by the hardware solution in business from the switchgears. What else we have? I had some questions actually here, because so when I show you the example of the internal classification and the cotton small rectangles that we are using for testing, this is an interesting topic, because I think I hear it very often that if you have internal classified switchgear, this is completely safe. And you have to keep in mind that it's not exactly like this. So you might as well, you might have to look into the manual, how to use it properly. Oh, I didn't wrote something interesting. So let me read it. So new EN 5010 to 2022 version, draft at B6.3. Additionally, other workers such as operators may be in reach of electrical arc hazard. These risks should be included in the risk assessment. For example, guidelines for the use of PPE IEEE 1584 guideline and ICTS 63107. See bibliography. So IC 63107, if someone doesn't know, is a standard for implementing arc mitigation techniques. I think it's called different, but that's more or less what it is. If you have arc flash relay, arc quenching devices, and so on, implementing in the switchgears. And this will be very interesting to see. I haven't actually looked into the draft, if that's available, so you can write me, drop me info about it. But it will be good. But from other side, I know that EN 5010 is something which sometimes in some countries is, I think the latest revision is from 2018 or 19 or 16, I think, but it might be that in your country the version you have now is the previous version, not the latest one. Okay, yeah, C1127 is for nominal voltage not exceeding 1000 volt AC. Okay, it's good. So, so to Aydin, to comment to Aydin, yes, it is good to know that it's coming there, and I would say it generally comes back to the topic when you need to have electrical safety plan, which I'm pretty sure it's generally similar requirements for every country, that you need to have your electrical safety procedures plan. For example, we have it in Poland under the government requirements, but it doesn't really specifically say about the arc flash, but just implement it where it's needed. But in every country it is there. So you need to have your idea what your system is, how it works, who is doing what kind of certification we need, who is the authorized personnel, and who can enter everything. So this is good to have. So what else we have? Let me check. Is there something in Q&A? No, we follow on chat. What I can say, it's from MIT's point of view, if we talk about the arc blast, it's a tricky part because arc blast is something which is hard to protect yourself against. So what we can do, we can calculate energy and we can calculate the pressure. For example, it's mandatory in Germany, most of them is mandatory in Germany to calculate the pressure for the building construction, just to find out if they will collapse or not. And on the other hand, it doesn't say anything about the people inside during the fault. But it will be very hard to protect against arc blast. But on the other hand, I haven't seen any proven accident or deadly accident that was purely caused by arc blast. If you have enough energy to cause arc blast, such big that it might kill you, at the same time there will be enough thermal energy that might burn you as well. So most likely, I would say it's if you focus on mitigation or limiting the energy, this would be probably the best reason also to lower the arc blast and make it safer. So Singh wrote aluminium versus copper bus, which is best option? For me, it doesn't matter really, to be honest. Aluminium has less expansion, so technically it will create less pressure because it will expand. I think it's 37,000 versus 67, or 47 versus 67,000 for copper. So generally it will cause less pressure inside, but it is more or less cost related. I think the only answer for the aluminium versus copper is more about the cost and your installation. If you have already aluminium, then you can go with aluminium. If you think you need copper, then yeah. I don't think the copper is the better one, but yeah. But if you would like to have aluminium, why not? You just need to have a slightly bigger cross section. I would say it's more about the pricing. I see there is a discussion about the C1127. I'm pretty sure it is up to 1 kV, but I will not get into this discussion because I will have to read it again just to find out which one is which one. So I will leave it to you, Antonio, Cesare, just to find out by yourself. What kind of myths you might have. So what I can tell you that, for example, it's not a myth, it's like misunderstanding when people are telling me about the PPE class 1, PPE class 2, PPE category 1, PPE category 2, and they are mixing things at the same time. So I will make a separate webinar, I think, about the PPE, but regarding the arc flash, just in general how to understand it. And keep in mind that there are two ways of testing in general. Which is open arc and box method. Box method is just testing. We have a small box, which is kind of trying to represent the switchgear or actually MCC drawer. And we have an open arc, which is generally easier because we can test 3 sets at the same time. And with box method, we can test only 1. And box method is very popular. It used to be very popular in Europe and was technically only one allowed to be sold here. While open arc was generally popular outside of Europe, in US and other countries, and everyone who would like to sell this in Europe has to do double testing. It was changed because now we have ELIM, which is energy limit, and ATPV and EBT 50 under open arc testing. ELIM is something which is allowed to be sold in Europe, and the difference is only that yes, we can. If you talk about the PPE category or PPE level, because there is, it is kind of NFPA mix. So I don't understand, to be honest, why in NFPA 70E there are 2 tables for PPE selection. They might as well, for me, get rid of one of them and our life would be easier. And I think protection would be at the same level. But nevertheless, we have 2. And we now follow PPE category when you use table method. So you have a PPE category 1, 2, 3, 4, which is not the same when you do arc flash study and you have a PPE level up to 12 calories and above 12 calories. And they are different. So it's something important to remember. It's more for engineers to explain it when they do study, but I see it very often that people refer to arc flash study and to PPE categories 1, 2, 3, 4. And it is clearly written in FPA that you cannot do it. You have to follow different table, which is up to 12 calories and above 12 calories per square centimeter. There are no categories there. It's like 2 levels, driven purely by the incident energy results. So something what I hear from time to time. It's not myth because some of the myths are generally coming from the US, but it's I would say it is about the in Europe. So in Europe, for example, you will hear very often that when I said about the switchgear, so low voltage, and I see that people have a problem with understanding, okay, why we generally do it. So it's not about the legislation, it's more about the safety improvements. So we would like to know if our system is designed well, protected well, and all of this has an influence to, we have 5 minutes left. So all of this has an influence to our safety. So that's why there are some requirements by IEEE 1584.1, how we have to do all the arc flash studies. And I try to follow this, doing all the recommendations, because that's the most important part. Technically, you can skip it, but it's not a good practice to do it. What else we have? So we have a time for last question because it's few minutes left. And now I have to stop the recording. Okay, I don't see anything, so it was a pleasure to have you all here today. And I hope we can see each other in September. That's when I will let you information know when and what kind of webinar, because I have few that I have to choose. And it's good that you all joined me today. It was great to have such audience, and have all safe and great holidays. And enjoy. Stay safe, and see you in September.